All right, everybody, welcome back. Next lecture video here for chapter 12. All right, so we're going to kind of partially continue our talk on intermolecular forces here by discussing some properties that you can kind of more visually see, right? So it's kind of, to a degree, difficult to really visualize these different intermolecular forces, right? We talked about dispersion forces that are the really, really weak forces that hold all molecules together. Then the next up was dipole-dipole interactions and their ability for polar molecules to have some kind of stronger force. And then lastly was going to be those hydrogen bonding types of interactions, right? So intermolecular forces that allow hydrogen bonding to fluorine, oxygen, and nitrogen to kind of create like the strongest possible intermolecular force. So what does that mean though, right? When you have a stronger or a weaker force or really any of these intermolecular forces, what do they allow these substances to do when they're stronger or weaker? Well, there's a couple of things. First of these properties is going to be something known as viscosity. Now, you might have heard of this term viscosity in the past, or if a liquid is considered to be viscous. And that's exactly what this is referring to. This is referring to the resistance of a liquid to flow. So long story short, the more or stronger your intermolecular forces, the more viscous that liquid ends up being. So now, when that word viscous gets used, again, the definition is resistance of a liquid to flow. Plain and simple, that just means if a substance is very viscous, that generally means that it's going to be slow moving, right? So think of, for example, a substance like water, right? Water, although it does incorporate and has a lot of different types of intermolecular forces, more namely hydrogen bonding. It's not a very viscous liquid, right? It's not very, very slow moving, right? It's very easily poured out of its containers. Now, on the flip side, you've got a substance like, let's think of something you might have used in the past, right? Let's think about something like pancake syrup or syrup in general, right? Maple syrup, right? Maple syrup is generally very thick. And if you were to put it in a cup or a container and turn the container over, it would take a little bit of time for that liquid to flow, right? So the more viscous or the higher the viscosity, the more resistance of that liquid to flow, right? So it means it flows slower when poured out of a container. So substances that have higher or stronger intermolecular forces are going to be very, very viscous and slow moving. Next up is something called surface tension. Surface tension is a pretty interesting one, right? It's the energy required to increase the surface area of a liquid. Now, you might have heard about something in the past where, a body of water, or maybe even a pool, something as basic as a pool, right? Surface tension is like the main reason why, guys, if you ever to, jump out of maybe off of a diving board or something like that into a pool, and you kind of stretch out and you almost kind of do like a belly flop into that pool. Surface tension is the main reason why belly flops hurt really, really, really badly, okay? Because what you're trying to do is you're trying to put an immense amount of energy and pressure on the surface area of that water to sort of break and increase the surface area of that liquid, right? Increasing the surface area of that water. Water has a lot, right? H2O has a lot of intermolecular forces, right? Very strong intermolecular forces. So that means it's got more and higher surface tension. Therefore, it's going to require more energy to break and sort of create a larger surface area on that top surface of that water, right? So that's why on the flip side, right, if you were to do more of a pencil dive, right, where you only have just your feet touching the water as you're diving into the pool, right, it's a lot less surface area you're trying to break and create a larger surface area with that water. So therefore, it requires less energy to actually kind of change that surface area. And the third and final one we're going to talk about is capillary action. And capillary action is when liquid flows through narrow spaces without external forces like gravity. So just like the previous two, the more intermolecular forces, the higher those, the stronger those intermolecular forces are, essentially that allows the liquid to flow a little bit easier in narrow spaces, right? It allows for better and more capillary action with that liquid. Now, different types of solids, right? Moving on to now the solids and liquids types of portion of this chapter here, chapter 12. So different types of solids are going to be things like atomic solids, molecular, covalent network, ionic and metallic, right? A number of these are solids that we've kind of touched on and talked about in the past here, more specifically the molecular and ionic and metallic ones. Now the type of solid, right? You've got all of these different types of ones, 1, 2, 3, 4, 5 of them. The type is going to be determined oftentimes by their intermolecular force. Now, when it comes to this right here, this is known as an allotrope. This definition says an element that exists in different structural forms at the same state of matter. An element that exists in different structural forms at the same state of matter. So, for example, guys, I'm sure you might have heard in the past that, you know, the diamonds, right? The gem diamonds, they're made up of just strictly carbon. So if you look at the periodic table, carbon number 6 right there on the periodic table is going to absolutely be exactly what diamonds are made of. Okay, diamonds are strictly made up of carbon. All right, now on the flip side, right, you guys should absolutely know what graphite is, right? Graphite's in a lot of your pencils that you guys utilize and write with on a daily basis while in school. Graphite is also made up of just strictly carbon. Well, again, if you look at the periodic table, carbon, you know, looks the same for the most part, right? This is where the idea of an allotrope comes into play, right? It's an element that exists in different structural forms at the same state of matter. Again, diamonds and graphite, both made up of just carbon, and they're both solids. Well, then what's the difference? How can we have such a wide difference in what a diamond is and what a graphite is? Okay, it's due to the arrangement, the structural arrangement of those carbon atoms. These crystalline solids arrange in regular repeating patterns called unit cells, right? That's what allows diamonds to grow in the way that they grow. Instead, you've got something like graphite. So we've got two different looks here in this video here, right? Looking on the right-hand side, this is top right-hand corner. This is exactly what a giant chunk of graphite just looks like, right? Straight up, just carbon. Nothing else happening here other than carbon present here. Well, same with our diamonds in the top left-hand corner. But when you look at the bottom left and bottom right, these are what these carbon atoms look like zoomed way, way, way down at the atomic level, right? So again, if we had the ability to kind of look at the structural makeup of these atoms at the atomic level, this is what they would look like. So the one on the right here, this sort of lattice-looking structure, creating these almost like, you know, hexagonal shapes here, regular and repeating, and sort of very, very basic, right? And they kind of allow for graphite to do exactly what it does, right? So yeah, very cool, very lustrous looking, but again, not nearly as intricate as one whole unit cell of diamonds. Okay, this whole structure here, encompassing literally 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 roughly different atoms of carbon are what put together this one single unit cell for exactly what one like little structure of diamond looks like. Okay, so this setup of carbon here, carbon atoms, is essentially one little structure, one unit cell of diamonds. So you need this to form in order for you to actually form diamonds, right? That's why, you know, diamonds only really grow when they're under immense pressure and heat, because you get these really cool, intricate looking patterns here that again are called unit cells. And again, that's the main difference, right? Both of them are solids, both are made up of carbon, but again, the makeup of their of their atoms, right? The makeup of the carbon atoms are so entirely different that they give rise to an entirely different substance. Now, the next half of this video, guys, is going to be dedicated to something called phase changes. Now, we're all pretty familiar with phase changes, right? They're when changes of state occur. And when you break it down, though, it's a lot more complicated than just changing from a solid to liquid, right? When it comes to taking an ice cube, which is H2O in the solid state, and letting it sit out on top of your kitchen counter for an hour, right? Over a period of time, of course, what you guys all know what happens is that solid ice, that ice cube, slowly melts to become a liquid. Again, that's super basic to us, right? But there's a lot more that goes into why that happens, right? Why that phase change occurs from solid to liquid. And what actually ends up happening is that these states of matter change and occur when enough energy is added to that substance, added in this case to that solid water, that ice is added to break apart the intermolecular forces that keep it together. So everything that keeps those solid H2O particles together are intermolecular forces. And when you add enough energy to that H2O solid to break apart those intermolecular forces, that's going to allow that water to finally move from the solid state to the liquid state, right? So now there's a lot more of a breakdown that occurs here. Again, no temperature change occurs during a phase change, however, right? It might seem like that's not the case, but I'll show you just shortly why that is actually the case. All energy actually goes towards breaking those intermolecular forces, right? So, and essentially, when I'm using that word energy, right? Energy ends up being heat energy in this case here, oftentimes. But again, all that energy, all that heat that goes towards melting that ice actually doesn't change the temperature. All it does is actually create those intermolecular forces in terms of breaking them. Now, phase change diagrams, phase change graphs are going to be what we use to kind of represent that and kind of view this happening here. I'm going to kind of go into detail about some of the notable parts of a phase change graph, phase change diagram, so you can kind of use that to kind of look at it in our next slide here. But for starters here, guys, the flat regions, the horizontal flat regions are going to correspond to phase changes. And in those particular regions there, that's when potential energy is actually going to increase during those flat horizontal regions, as again, all that heat energy goes towards breaking intermolecular forces. So again, when you see this graph, which is literally x-axis time, y-axis as temperature, you're going to literally see a flatlining of, again, a horizontal line indicating a phase change. And again, that just means that temperature is not going up. Now, kinetic energy, aka temperature, right, increases during the sloped regions, right? So those angled regions, they're going to be going, they're going to have actually some verticality to it, right? All of that energy is going to go towards making the particles move faster, therefore raising the temperature. Because again, as we know, the definition of temperature is the average kinetic energy of the particles. So now this is, guys, what a phase change diagram or phase change graph looks like. Again, we can basically look at this x-axis. I know it says heat added, but we can also look at that as time as well. The y-axis is going to be temperature. So as we see, as we move from point A to point B here, this substance is still, okay, we're talking about a phase change diagram, by the way, for water. From A all the way to B, this is still straight up ice, right? It's water, but at the solid state. Up until we reach point B, however, this substance has been below 0 degrees Celsius, which means it's absolutely been ice. But as we go from left to right, from A to B, heat is being added, the temperature is increasing, and eventually we reach point B. Line BC, which is between point B and point C, is a phase change from the state of matter of solid to the state of matter to liquid. And that's going to essentially be what happens from point B to point C. Heat is still being added as we go from left to right here. But as we see, temperature is very much staying the same. It's staying at 0. No change in temperature is occurring here until we officially reach point C. And then all we have here is liquid water, which then at that point can start to increase in temperature from 0 degrees Celsius all the way to point D, which is at 100 degrees Celsius. And as we know, 100 degrees Celsius is exactly when boiling occurs with water. So line DE represents, again, another flat line region where that boiling starts to occur. Our state of matter changes from liquid at D to gas at point E. And again, the temperature is remaining the exact same. Nothing happens with temperature. But all the while, heat is still being continued adding from left to right, from point D to point E. Eventually, guys, once all that water has changed from liquid to gas at point E, that's when that gas can start to increase in temperature again as more heat is being added left to right there, okay? So this is a pretty, great example of what a phase change graph is going to look like. You guys will definitely do an example of one of these in class, so look out for that. Now, when it comes to heat for phase changes, there's a couple of definitions here. I'm not going to spend too much time talking about heat of fusion, heat of solidification, or heat of vaporization, but these are just sort of specific measurements that have been taken over time that scientists have collected that kind of tell you the exact amount of heat required to either melt a substance or freeze it or also vaporize it. And that's where we get fusion, solidification, and vaporization from. And then lastly, a couple of differences between evaporation and boiling. Now it might be, and we'll finish up with this slide here. Now, evaporation and boiling, right? Both of them, terms that you guys are relatively familiar with, right? When it comes to evaporation is liquid to gas. Boiling, also liquid to gas. But there's some very key differences between evaporation. Evaporation, guys, is not dependent on temperature or vapor pressure. It's literally just sometimes water molecules escape from these, liquid molecules escape from the surface of the water, changing it from a liquid to a gas, whereas boiling encompasses a lot more, right? Vapor pressure, essentially of the liquid equaling the atmospheric pressure. Okay, that's about it, guys. I'll see you next class.